Hi, welcome back. Just like we did with the CTFT, we have to handle periodic signals differently when calculating the DTFT as we would aperiodic signals. So let's take a look at how we can calculate the DTFT of periodic signals. First of all, let's try to understand why do we have to handle them differently anyway. So the Fourier transform is defined like this. Okay, I'm going to take x of n, multiply it by e to the j omega n, sum over n equals minus infinity to infinity. That gives me the Fourier transform. But there's an issue. If x of n is periodic, then it goes on forever. And so what you're going to find is that this sum for minus infinity to infinity, which also goes on forever, then will not converge. And so you will not be able to find the Fourier transform of any signal that goes on forever, i.e. periodic signals, using this equation. You can't do it. That's why we have to handle periodic signals separately. All right? So we're not going to do it that way. So the first thing you need to ask yourself is the signal I'm looking at periodic? If it is, then you have to do something different. Now let's remind ourselves what we did for continuous time periodic signals. We said that the Fourier transform was 2 pi times an infinite sum of the Fourier series coefficients times delta functions that are spaced by omega 0, where omega 0 is 2 pi over the period of the periodic signal. So if you don't recall this, then you should go back and just refresh yourself about the continuous time Fourier transform of periodic signals. This is what this is the conclusion that we had in that video. So we're going to suggest something similar for discrete time Fourier transform. That is, the discrete time Fourier transform is 2 pi. It's actually the same thing. It's actually the same thing, where omega 0, though, is 2 pi over n, right, where n is the period in samples. So this is our Fourier transform. And so, of course, we need the Fourier series coefficients. And the subtle difference between the two, discrete time and continuous time, is to recall that the Fourier series coefficients are periodic with period n. So as long as you can remember that, then you should be able to apply this equation no problem if you're used to the continuous time counterpart. So let me give you an example. Let's say that our sequence xn was, and we'll just stick with this basic complex exponential, this basic sinusoid, this guy. Okay, this has a period of n equals 5 and omega 0, a fundamental frequency of 2 pi over 5. Okay, so and then this is already as a sum of exponents, right? So this is in the form e to the j omega 0 n, and so we can this is the first harmonic, right? Because it's 1 times omega 0, and so we can read off right away that a1 is equal to 1 because there's an implicit 1 there. So that's the Fourier series coefficient. It's very simple. It's almost trivial. That's the Fourier series coefficient. But you have to remember that not only is a1 equal to 0, or is a1 equal to 1, but then a6 is equal to 1. How did I get a6? Because these things have to repeat every 5 samples. So if or every 5 coefficients. So if a1 was 1, then a6 is 1. A minus 4 is 1, right? And a11 is 1, and you can you can continue on going plus or minus. Those are all 1, and that's all a consequence of frequencies differing by integer multiples of 2 pi are the same. Okay, so let's put this all together now. Let's see if we can sketch what the Fourier transform of this thing would be. And so here's omega. This is going to be x of e to the j omega, Fourier transform. So I need to evaluate this sum. So this becomes 2 pi times a sum from k equals minus infinity to infinity of ak's delta of omega minus k times 2 pi over 5. Right? And what are the other values of ak? Well, the other ones are equal to 0. The ones that we haven't listed are the ones that are not 1 plus k times 5. So the other ones are 0. There are no other frequencies present. So in the sum, for example, the k equals 2 term, a2 is equal to 0. So there's no impulse at 2 times 2 pi over 5. And so all we need, for example, the k equals 1 term, we would have 2 pi times a1, and a1 is 1, delta of omega minus 2 pi over 5, right? Well, what is that? That's an impulse at 2 pi over 5 scaled by 2 pi. So this is 2 pi over 5. Great, so this impulse represents there being energy at the frequency 2 pi over 5. Of course there's energy at the frequency 2 pi over 5, right? But also, we would add that, this is a sum, so we need to add to that the impulse a6. So a6 is, k equals 6, 2 pi times a6, a6 is 1, times a delta function of omega minus 6 times, this is the k equals 6 term, 6 times 2 pi over 5, so 12 pi over 5. So we find this is an impulse that's shifted by 12 pi over 5, and so maybe this is 12 pi over 5, and it's scaled by 2 pi. So we're saying that this thing, even though there's no 12 pi over 5 explicitly listed there, has energy at 12 pi over 5. Well, why does it have energy at 12 pi over 5? Because what's the difference between 12 pi over 5 and 2 pi over 5? That's 10 pi over 5 or 2 pi. So these two frequencies differ by 2 pi, which means that they're the same frequency. So if I had energy at 2 pi over 5, I better have it at 12 pi over 5, right? And you continue on this way. For example, the k equals minus 4 term, right? We would have to add to this the k equals minus 4 term. This is 2 pi times a minus 4, which is 1, times delta of omega plus, because k is minus 4, 8 pi over 5. What is that? Well, that's an impulse that's been shifted to the left, 8 pi over 5. So that's over here somewhere. Scaled by 2 pi. And this is minus 8 pi over 5. So I don't see an 8 pi over 5 here, or minus 8 pi over 5. Where did that come from? Well, again, the difference between 2 pi over 5 and minus 8 pi over 5 is 2 pi. So those are the same frequency. So I better have energy at minus 8 pi over 5, and so on. So you continue on this way. They're going to be they're going to be spaced by 2 pi, right? And they have to be spaced by 2 pi because the discrete-time Fourier transform is always periodic with period 2 pi. Anyway, we'll look at more examples of this, but the takeaway, this is not an example video. The takeaway from this is that the Fourier transform of a periodic signal is exactly what you would expect from continuous time. You just have to remember that the Fourier series coefficients are periodic with period n. So I will see you then in the next video. We're going to take a look at a couple more examples.